Okay, so here we go. So for section 4.1, number 11 is about an elevator that's descending and it's got a lamp hanging inside the elevator. Okay, fancy hotel or something. All right. So this one you gotta read it carefully. The elevator is descending, moving down, so the velocity vector points down, and it's decelerating, which means it's slowing down. So my velocity is getting less negative. So which way does my acceleration vector have to point? Up. Which means that my net force vector also points up. Follow? Okay, so let's see what we know. So we know that our acceleration is 2.4 meters per second squared, and it's got to be positive to counteract the downward velocity. Let me pause there for a minute. Is everybody good up to there? All right. I said, I don't remember. I said that the acceleration has to be positive, upward, to counteract the downward velocity of the lantern, or the lamp. Good? All right, so what forces act on this thing? There are two forces. What do you got? Gravity's pulling it down, and tension's pulling it up. The problem tells us, in part A, it tells us that the tension is 89 newtons. And then we want to find the mass, right? Okay, so we can write here two expressions for net force. What I'm about to do is a super common problem-solving strategy. Two expressions for net force. Mass times acceleration equals total force. So let's see, my total force is going to be 89 newtons plus mass times negative 9.8. Right? Because this is just mag or mg, right? Oh, and I know the acceleration, don't I? So this becomes mass times 2.4 equals 89 plus mass times negative 9.8. And solve it. That is super common. Two expressions for the same thing. Okay? We have two ways to find net force. Mass times acceleration, total force. Set them equal to each other and solve for the missing thing. Good, you guys? All right, I believe that number 14 is very similar to that. I think you have to use kinematics equations to find the acceleration, and then it becomes the same problem. Okay, 14, or sorry, what do we got? 11b. What is the cord's tension when the elevator ascends, as in moves up with an upward acceleration? So, sorry, I know. All right, so we found the mass. I was super conscious of it as I said it. All right, so our mass is 7.3 kilograms, right? Everybody good up to there? All right, so, oh, darn it. All right, so for 11b, here's the deal. We've got a lamp that's got a mass of 7.3 kilograms. I can find my force of gravity. It's just going to be 7.3 times negative 9.8, whatever that is. Let's see, what does it say? What is the tension if it's accelerating upward with an acceleration of 2.4? So it's accelerating upward with an upward acceleration. So my acceleration is positive 2.4. So we ought to be able to solve it, right? Mm-hmm. It's the exact same thing, though, isn't it? That's why it was a smiley face. Because look, whether you're moving up or down, your acceleration is still the same positive acceleration. So you have to have the same net force, which means the same tension force, right? Because your gravity hasn't changed. So, I mean, I guess you can go through and solve for it and find your tension force, but you're just going to end up getting 89 newtons because you've still got the same acceleration. Right? Because in both cases, your acceleration is becoming, your velocity is becoming more positive, right? Yep. In part A, it's getting less negative, which is equivalent to getting more positive. And then in part B, it's just getting more positive. So, Sarah?
All right.
You sure?
Yep.
All right. Are we good with 11?
Yeah.
All right. So I lied. 13 is the same as 14, except you got to use some kinematics equations to find the acceleration. But same basic idea. All right. 14. There's not a whole lot to do with 14. So 14 says at time t equals 0, a constant force F begins to act on a rock moving through deep space in the positive x direction. And then it gives you some functions. And then it says which ones are possible functions for the rock's position. So you've got, a rock. Okay? You've got a constant force on it. Now, if we assume that the force is not 0, then what's going to be true? It'll accelerate. And if the force is constant, then the acceleration will be constant. So to find out which ones are right, you're given expressions for position, so just decide if your acceleration is constant. How do we do that? Take the derivative. The first derivative will give you velocity. Second derivative will give you acceleration. So if your second derivative is a constant number that doesn't depend on t, then you're good. Okay? So let's check it out. So for number 1, position of time is 4t minus 3. That means my velocity at time t is 4. My acceleration at time t is 0. So that probably doesn't work, right? Because this would be accelerating, right? So similarly, when you do 2 and 3, you get accelerations of -8 and 8 respectively. Did I do that right? Yeah. So those are good. And then B, which function is f directed in the opposite direction? Well, it's got to be the one that gives you the negative acceleration, right? So 2. Cool? All right. All right, we had a couple others up here. 12 and 10. 10 is worded badly. I think if you understand the lamp one that I did.
Is the 10 centimeters supposed to be like the displacement?
Yeah, so 10 is misleading because it doesn't, I think you need to assume that you're pulling the fish horizontally. And it doesn't make that explicit. I need to reword that problem. I stole it out of the book, which I stole all these out of the book. So let's not worry about 10. That was just worded badly. Oh, number 6 has a smiley face. So I'm going to read it. Think for a minute. Don't shout out an answer. A ball with a weight of 1.5 newtons is thrown at an angle of 30 degrees above the horizontal with an initial speed of 12 meters a second. At its highest point, what is the net force on the ball? Come up with an answer in your head. Here are your choices. Are you ready for them? Multiple choice. A, B, C. I'm not going to put units on them. Well, I guess it would have to be newtons, right? Because they're force, right? Does everybody have a choice that's up there? Okay, what do we got? Good, it's C. It is C. 9.8 is the acceleration at the top of the path. Right? All right, so let's run through this. Check it out. So you've got a projectile that's flying through the air. Here are the things you're told. You know the initial velocity, you know the angle, none of that garbage matters. You are told that the object has a weight of 1.5 newtons. What's the symbol for weight, you guys? Velocity is v. What's weight? What's the definition of weight? I'm going to go back and change all your honors grades to F's. What's the definition of weight? Force of gravity. The definition of weight is force of gravity. So here's the ball at the top of the path. What's the only force on it? Gravity. Or, what's the only force on it? Weight. They're the same thing, right? The problem tells you the weight. What is it? 1.5 newtons. There's your answer. Yeah, Peter, and then I want to come back to what I just overheard Carlos say. Peter, go ahead.
Wouldn't it not matter what, what?
There's a whole bunch of garbage here. Yeah. That's the net force the entire time it's in flight.
Because it never accelerates.
Because the entire time it's in the air, it's in free fall, and so the only force is gravity. So DAP indeed. Are we good? Okay, so remember, this is the weight. Why is it not in kilograms? What does kilograms measure?
Mass.
Mass. So please remember, mass is an intrinsic property of an object. This sea clamp here is made up of 7 bazillion molecules. Those molecules have mass. If I take it to the moon, I've not changed the number of molecules, and therefore I've not changed the mass.
It's an exact calculation.
It's exact. I counted them this morning. All right. So when I take it to the moon, why does it weigh less on the moon? Because there's less gravity. Good? Good? Was that what you asked before? No.
I just don't understand why you give us them in newtons and then we have to convert them into kilograms.
So there's a relationship between weight and mass, which is this. So you should be able to, if I give you the mass, you ought to be able to find the weight. If I give you the weight, you ought to be able to find the mass. Okay, I think some of that's because you, yeah. All right, are we good? All right, so I think the only other one that I want to talk about, shoot, we need to finish the notes from the other day. Lady number 12. I'm going to do it quick. 12, a firefighter weighs 712 newtons. So here's my firefighter. He's got a cool firefighter hat. It looks like he's got a butt on his head. Deal with it. All right. All right. Here's the pole. I'm going to just pretend that didn't happen. We're going to just keep moving on like everything's normal. All right.
I'm sure you're going to fight fire, or is he a different kind of fireman?
That's kind of I requested, yeah.
Well, now I'm struggling because I got to draw on the force of gravity, and I'm gonna draw it over here. All right. So there's your force of gravity. All right. It says he slides down the vertical pole with an acceleration of 3 meters a second squared. This is exactly the same as the elevator problem, right? Yeah. So my acceleration is going to be 3 meters a second squared. Positive or negative? Yeah, it says he slides down the pole with an acceleration of 3 meters a second squared directed downward. So his downward velocity is increasing, right? So find your net force. The other force on him has got to be the vertical force from the pole. Force from the pole. So once again, you're going to do MA equals negative 712 plus the force of the pole, right? And solve for the force of the pole. Oh, wait. Oh, gotcha. So this maybe is where Carl is getting tangled up. I don't know the mass, right?
Correct.
But we can find it, right?
I'm
Okay.
fine with this problem. This isn't.
Oh, okay.
Yeah.
All right. So is that okay if I say that and stop here with that one? B, what's the magnitude and direction of the... Oh, gotcha. So I probably should have put this later because we haven't done third law yet. But yeah, so 12B, the idea is the pole is pulling the firefighter up. B is saying, well, that means the firefighter is pulling the pole down. So the forces should be equal and opposite, right? So the answer to B ought to be negative 494. Good? All right. So like I said, numbers 16 through 19, I have videos up. So let's just get a quick show of hands of how many people need to see different ones. So 16 through 19, how many of you need to see 16? 2, 3, 4, 5, 6, 7, 8, 9. Okay. How about 17? 1, 2, 3, 4, 5, 6, 7. How about 18? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. How about 19? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. All right. Okay.
I think it's more so I have to try hard.
All right. So I tell you what, you guys. Let me do this. I want to make sure we finish up the notes from yesterday because I want you guys to be able to try one of those drag force problems over the weekend. Okay. So let me see if I can finish the notes, and then if we have time to do a couple of these, I'll do them. If not, did you guys all see where I found the links for the videos? Yeah. So why don't you, over the weekend, you can look at the videos if you want. The quality is varying. If they're terrible, let me know, and I'll go back and re-record them, because they were all done last year. And then if I need to spend more time with them next week, I'm happy to do that, okay? Sound reasonable?
Yeah, sounds more.
Everybody okay with that? Okay, cool. All right, so we're going to pause the homework. We're going to move back to the notes from yesterday. All right, so here's the deal. I talked to some of you. Some of you guys were like, yeah, that kind of made sense. I feel like if I sat down with the notes and tried to work through a problem and did it cookie cutter style, that'd be okay. Some people were like, I have no idea what was going on. So we're just going to kind of keep moving forward and see how things go. This is just my second year with this. I'm trying to figure out the best way to approach it. Maybe I should have waited on this. I don't know. But it sort of conceptually it fits in here, so that's why I chose to do it now. I guess again I will reiterate that the process is exactly the same for all of these. All right. So process is. Wait a minute. Process is I'm dumb. I'm going the wrong way. Stop it. All right. There we go. Okay, so here we go. I said, here we go. There we go. Oh, darn it. All right.
Here we go.
Okay, so step number 1. Write an expression for your net force. And then set that equal to MA. Okay, that's step number 1. Step 2, replace the A with dV dt. And then voila, that's your differential equation. Good? All right. Step 2 is, I think, the hard part. That's where you take this differential equation, put all of your dt's and t's on one side, all of your v's and dv's on the other side, and then you got to integrate. And I think that's going to be the tough part. I think that's where people are going to struggle, and I think it'll just be, you'll get it the more you practice. Okay? So, do I need to go back and say anything? Yeah, what do you got, Patrick? I'm sorry?
I'm confused with step 1.
Step 1 up here?
Yeah.
Okay.
So,
Thank you for being honest.
okay, so like in the homework on number 2, I didn't really know what to do. Like the answer is dV and dt.
Okay, let me hold off on the homework for a minute, please, because I think you're probably the only one who's looked at it. Is my guess. Okay, and I don't want to spend time on it until people have had an opportunity to think about it a little bit. So A, I'm super glad that you're like working ahead and like, oh, we learned this stuff like yesterday. Let me try it. So like super thumbs up. And I want everybody else to be on the same page before we go over it. So let me kind of keep doing what we're doing here. So you said you don't understand step number 1. Do you understand this step number 1 or no? So the process was this. I knew that the astronaut was throwing this happy little apple to his buddy, right? because we're in the space station, we don't need to worry about the effects of gravity. The only force on the apple is this drag force, right?
Oh, I think I get it. Kind of.
So all I did was I wrote two expressions for net force. One which represents total force. Oh, well, my total force is just the drag force in this problem. So this expression represents all of my forces added up. Good? The other side of the equation is just Newton's second law, mass times acceleration. This side will always be the same. Good?
Yeah.
All right. Then you replace A with dv dt, and there's your differential equation.
Oh, okay.
Okay? And I mean, you can, here I solved it for V, whatever, it doesn't really matter.
Oh, okay, I think I get it. We down the homework, I didn't really account for gravity.
Gotcha. Yep. Yeah. So the ones on the homework are notch up from here, but
The mass goes away when you.
yes. Yeah, your masses will cancel out. Exactly so. Oh, actually, no, they won't, because they won't cancel out of your FD.
It just cancels out the gravity mark.
Right.
And on that.
Okay. What's up, Seba?
Where are you getting the B?
It was given to you in the original problem. You were told up here that your drag force was equal to negative B, which is some garbage constant that we don't care about,
Oh, I see it now.
times V.
Okay. All right, so I get it.
Everybody good? All right, cool. So once you've got this equation, you've replaced your A with dv dt. Step number 2 is get all of your V's and dV's on one side, all of your T's, which there won't be any, and dT's on the other side. Good? So that's basically just some algebra, and you land here. Okay? So everything that I did between here and here was just rearranging variables. Good? Then you integrate both sides. Okay? So you literally, the only thing I changed between here and this next red step is I drew in, oh shoot, I wanted that to be a different color so it would stand out. I drew in integral lines. Okay? And then I guess the one other thing that I did is I moved the integral. This is a constant, right? Was everybody okay with why I was able to move the integral from here to here? So everybody's good up to there? All right. So once you draw on your integral lines, then you ask yourself, all right, well, where does my problem begin and where does it end? All right. So for this problem, in terms of time, my time began at time 0, and I want to figure out what's going on after random time t. Cool? And during that same time, my velocity went from v0, whatever the starting velocity was, up to whatever the velocity is after that amount of time at t. That was a weird sentence, but you know what I mean. There's like too many syllables in there. Good? All right, so then is the integration part, and that's the part, well, I mean, all of this is going to take practice, but like, so what was the big sort of revelation that we had yesterday as we were learning how to take this integral? Do you guys remember? The integral of dv over v is just natural log of v, right? Okay, and then Margaret's right. On the other side, the integral of dt is just t. Cool? Everybody on board? Sarah, what's up?
That's okay.
You sure?
I'm kind of lost. I'll figure it out.
Okay, at least try the problems. That's why I'm giving you one a day. So you have an opportunity to try it, and hopefully you'll make little baby steps each day.
Okay.
And by the end, you'll get it. I'm hoping. We'll see. And even if not, I mean, the test isn't for, we'll get there. Okay. All right, so the integral of dt is just t. Integral of dv over v is natural log of v. Good? And then we know our bounds that we're evaluating at. So then so from here to here, I just plugged in my bounds, right? T is going from 0 to t. V is going from v0 to vt. So anyway, simplify, simplify, simplify. So eventually you're going to come up with an expression that just says t equals blah, blah, blah. Cool? And then it's, I say just. I understand that it's not just, but I'm going to say it's just algebra from that point forward. Okay? So you got to then solve for t. So you got to get rid of the natural log. So remember, we decided that e to the and natural log of are inverses, right? One always undoes the other. Just like squared and square root, or sine and inverse sine. Good? Okay. So, algebra, 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 and you land here. All right. Is there anything that I can say right now that would help clarify, or is it just at this point you got to sit down and try it on your own?
Oh, yeah, try it. Try it.
Okay. All right. So, that was all part A. No, sorry, that was part A and B. A and B. So, are we good up to there? All right. Part C says, how much time will it take to get to a velocity of, I think VF it says, right? Okay? So all you're going to do is put VF in here and then solve for T. All right? So I'll say two things. So if you choose to do it that route, I'll show you a super secret ninja shortcut in a second. But if you choose to do it that route, you plug VF here, and then solve for t. So you would divide by v naught. How do you get rid of the e?
Natural log.
Take natural log, right? And then solve for t. It's not bad. Or, super secret ninja shortcut. Patrick, you good before I scroll up? What's up? Talk to me.
So plug in VF for PT.
Yeah, so the question is asking you, how long, so it's asking you to write an expression to find out how long it takes for the velocity to get to some arbitrary value, VF. Okay? So what I'm saying is, suppose it says how long would it take to get to a velocity of 5? So you would put 5 here equals this mess. And then just solve for t. Okay? But it's not telling you that it's 5, it's just telling you it's some arbitrary value some arbitrary value VF. And solve for t. Good? Thank you for being honest when I was making sense. Are we good? All right. Maggie's going to tell me a better way to do it, or do you have a question? You're not at all. This is hard, you guys. Don't beat yourself up. This is the real deal. This is like, most students don't get this till they're a sophomore in college, so like, you're killing it. What do you got?
What D is, and how could you solve for VF?
You're,
Still very.
yeah, I mean, it's the same thing like, in whatever, in algebra, sometimes you have an equation that's, whatever, A equals 3B minus C over D, solve for D.
Oh, okay, so you just leave all the variables.
Yeah, so you just leave the letters in there and rearrange them. It sucks, but that's what you gotta do. Follow?
Yeah.
Okay, you're not dumb, you're good. It's hard, this is not easy. Carla.
So on the next one, we're solving for t, and we had, like, when we were doing the simplification up there, we already had it.
Yeah, okay. So you can do this, you can solve for t, but Carla has just discovered the super secret ninja shortcut, which is this. Check it out. Look, when we did our work, way up here, we had an expression that said t equals. So I'm going to replace v of t with whatever that vf is that you're trying to get to. Follow?
Yeah.
Adam?
So the
Good job.
The next question is how long will it take to stop? So instead of saying VF, we would just say 0.
Exactly. So I want to reiterate what Adam just said, but before I do, is everybody good with the realization that Carla just made about if you follow the process back, at a point during our process, we wrote an expression for t, so use that. Cool? All right? And so then Adam took that one step further. Problem 4 says, how long will it take to stop? That's, well, me too. But what's it really asking you? It's asking you how long it takes to get to a VF of 0. So just put 0 in here. Now,
Natural log of 0 is 1.
natural log of 0 is 1, is that right?
Yes.
No.
No.
Natural
No,
log
I
of
think the
1 is
natural log is
0?
0.
Did I say
Natural log of 0 is undefined.
I knew that.
So when's it going to stop?
No.
Never.
Oh, what?
Never. Okay? Because the idea is it's always moving, it's always slowing down, but it never hits a velocity of 0.
Wow.
Okay? Yes, and then yes.
So, would there be, wouldn't it technically travel a distance in infinite amount of time, kind of? Because I'm thinking about like infinite series.
Yeah, well, that's the next question. Is how far does it go? And it's weird. There's a finite distance, but it never stops.
Okay, that's what I'm thinking.
Yep, that's exactly the next question. All right, so hold on. We're not there yet. Let's just focus on the it never stops part. Okay? Yes.
I was just looking back at the questions that were asked and then looking at the work. So what would be the answer for 1 and 2 out of all the work that we just did? Like,
For problems numbers 1 and 2.
yeah, for this.
So problem number 1 is this. Like, I don't mean this in a snarky way, but right before I wrote 2.
Oh, okay, that's
Good. I didn't mean that to sound. I know there's a lot. I get
okay.
it.
So I just wanted to make sure, like, I wanted to make sure it's all different.
Okay, so that's number 1.
Okay. So that's just the velocity, like, and then okay.
Good. Everybody good? All right. Number 2 is that's the big part. That's the hard part. Number 2 is all of this garbage all the way down to here. So that's the answer for number 2. Good. All right. Yes.
Could you go to the part where you take the division and make it subtraction?
Yes. So that's a natural log rule. There's a rule of
Yeah, I just want to see what it looks like.
yeah, but just real quick so that everybody knows what I used there. It turns out that the natural log of A minus the natural log of B is the same as the natural log of A over B. That's the rule that I used. Okay? And the process looks like this. So the M over B stayed. And inside my parentheses, I had natural log of VT minus natural log of VO. And I just rewrote it as natural log of VT over VO. Follow? Okay, and like Patrick says, you don't have to do that step, because you said you solved it without doing that rule, and great, that works. Are we starting to fill in the blanks a little bit?
Yes.
Some? This is tough, I get it. All right. Okay, so is everybody okay with how to find the time to get to a certain velocity? You just plug that velocity in here. Cool? And is everybody cool with the fact that the natural log of 0 is undefined? No? Do you guys would it help if I talked about why it's undefined or no?
Probably not, to be honest.
Let me show you real quick. It'll take 2 seconds, I promise. And I'm hoping it'll shed some light on it. All right? So check it out. What do you mean when you say you don't know what's going on?
You know, like when people like explain why,
Oh.
sometimes it helps. I don't know.
Okay.
I'm gonna not,
Here, check it out. Suppose I gave you this function, y equals e to the x. Is there a value that I can put in for x and make y 0? No. Okay? Now, if I take the natural log of both sides, I get the natural log of y equals x, right? So, I can't get 0 here. That means I can't put 0 here. That's it. Like, that's why. Cool? All right.
I agree, Dog.
Okay. So that's why, how long will it take to stop? It never stops, because you'll never get to a velocity of 0. All right. Finally, number 5. How far will the apple travel? Yes. I heard my name. All right. Okay, so here we go. So I've got an expression for velocity at time t. It's this. V naught equals negative bt over m. No, it doesn't at all. It's v naught equals, or v of t equals v naught times e to the negative bt over m. All right. So how do I write an expression for the position at a certain time? Yes, you do have to integrate it. I'm going to hold off on this. I think you guys need to process this. I'm going to hold off on this. Let's come back to example 5. I don't think it comes up a ton. I think your brains are going to melt if I keep going.
And if we don't understand it, then we'll just be like, all right.
How many of you want to see it? How many of you want to wait and process? Just do it? All right. Oh.
Close your eyes.
Yeah, I'll get them back. Yeah. Okay, so I'm going to do it quick. All right. So my position. So how do I want to do it? Let me do this. My displacement is going to be the integral of v of t with respect to t, right? And I want to find out how far it goes between a time of 0 and a time of
T.
Yes, you can do it that way. Or infinity, right? Either way works. You can either put t here now and then plug in infinity later, or you can just put infinity. Because the idea is it's never going to stop. So that means no matter how much time goes by, it's never going to stop. So let's see how far it goes in that time it takes to never stop. Which is a weird sentence. Okay? So real quick. What's the derivative of e to the x? Do you guys remember?
Yes.
E to the x. That's why e is special. E to the x is the only... Oh, shoot, that's not what I wanted to do. E to the x is the only function in the universe where the derivative of the function is the function. At any given point, the slope of the function is the same as the value of the function. Like, that's a neat thing. Okay? So, we want the integral from 0 to infinity of, I'm going to pull my v naught out because it doesn't affect anything, e to the negative bt over m dt, right? Yes? Sorry?
The answer is v naught, right?
I don't know because I haven't done it yet and I don't have my notes sitting in front of me.
Because e to the negative infinity is...
Yes, but e to the... you might be right. You might be right. All right. No, you're not quite right. You're missing one little thing. You're warm. You're warm, though. You're warm. Okay, so what thing do I take the derivative of that'll get me this? Well, it's got to be e to the negative bt over m, but if I take the derivative of that, you got to do stupid chain rule.
Oh my god, I hate the chain rule. Yeah.
So what's the derivative of negative bt over m?
Oh, come on. What? So B and M are so
What's the derivative of that?
Negative b over m.
Negative b over m, right? So I got to get rid of it.
hang on. I need you to like narrate this far.
Go ahead. What are you saying, Seba?
Can you explain that one more time?
Yes. All right. So, yeah.
Isn't it b over m and not m over Oh, is it?
Okay. So our question is, what thing do we take the derivative of to get this, right? Okay. So check it out. So if I take the derivative of e to the x, that just gives me e to the x, right?
Yes.
Okay. If you take the derivative of e to the 2x, it gives you e to the 2x times the derivative of this, which is 2. Follow? So here, if I take the derivative with respect to t, of e to the negative b over m times t. So the 2 here is now being replaced by negative b over m. Good?
So you just,
Cool? So then I had to multiply by negative m over b so that it cancels the negative b over m.
Oh, the negative b over m that would result from the chain.
Yes.
Oh my god. I hate chain rules.
I know.
This is like February.
Sorry guys, I know it's a thing. We got to get through it. It's okay though, because we have months to learn it. So we'll practice it. We'll keep coming back to it. It's okay. Patrick, what do you got?
Would it be negative MD?
I don't know yet. You're way ahead of me. I just want to make sure everybody's okay with the integral. All right. Okay. So if I'm sensing we lost some people. Let's finish it up. We'll have time to do cleanup. All right. Okay. So that's my integral. Don't forget we're multiplying it by v naught. And now you just plug in 0 and infinity. Okay? So, e to the negative infinity is, what's anything to the negative infinity?
quite strong.
Approaching 0, but not.
E to the negative infinity is the same as 1 over e to the infinity.
Almost zero.
So it's 0, right?
It's a limit.
Good? It's all connected, yes, just like dirt gently. All right. So you get 0. You get 0 minus. Now I got to put 0 in. What's e to the 0? E to the 0 is 1 times VO times negative m over b. The negatives cancel, and you get m over b times v naught.
And that's your answer.
Literally, we did all that.
Ah, too many people. You go.
Does that mean that the object is floating because it's infinitely not
Well, it's
moving?
floating because we're in a space station
That's what I mean.
where there's no
but
gravity.
when you're saying that it's not moving, there's no displacement, but there's time.
No, it's still moving.
But you just said that there's no displacement. Didn't you?
That is the displacement.
Oh, okay.
Yeah, this is my displacement.
I misunderstood the 0 part.
The 0 is, yeah, the infinity part. Okay. All right. So time is up. So here's the deal. Monday, we're going to do this lab, I think. All right. So here's what I would like you to do for Monday. Try the first 4.2 problem. Why is it number 2?
The first one's just like conceptual.
Oh, gotcha. Okay. So do numbers 1 and 2 on 4.2 for Monday.
Mr. Hacker, I have a question about number 2. I was able to get positive 17. That's because I think I'm stuck in this conception of force.
I didn't know they sold it before last year.
I was thinking air resistance is opposite.
No, so we're not going to talk. So G is understood to be positive 9.8. So when you're working with it, you need to manufacture the negative by putting it in. Shoot, I hope I didn't make a mistake. So you got the right answer except for the G.
Because I figured air resistance was they decided to make gravity would make them
3 weeks.
You're right. That's totally got to be.
What else?
Right now,
One of those needs to be positive, depending on how you define your positives and negatives. So now to remind about that. You're 100%.
I think you should go through it just to make sure.
Yeah, I will. I don't know who's next.
I just have a really important question.
Yes.
I'm making a student film, and I was wondering if you would
Sure, yes, I would.
probably play yourself. I would play yourself. It starts out taking points.
Okay. Yes, I can do that. Will I be in any way ridiculed or look stupider than I usually look on a daily basis?
No, it's about as Okay, so we'll give you a script. All my questions are figured out.
Okay.
Thank you for agreeing.
Yeah, absolutely. I'm honored. Thank you for asking.
This question's probably a little long.
That's okay.
Yeah.
Where are you going?
How do you find, like,
I don't know, I may.
weight, like, how does it relate to masculine?
Wayne's
Sorry, I just realized I'm still recording.
Where are you though?
Okay.
I'll be in the.